Hello, my name is John Smith. I'm an IBM Fellow and Manager of AI Tech at IBM Research. So today I'm going to be talking to you about some of the work that we're doing at IBM Research in AI. So technology is moving at an incredible pace. And no technology is moving faster today than artificial intelligence. So if we look back over the past decades, there have been tremendous advances in AI on topics like expert systems, on machine learning, but more recently on deep learning. Let's take a look at how we got here. There was something known as the deep learning revolution that kicked off in roughly around 2012. Actually, there's a particular task that was addressed by researchers at a university. It was the University of Toronto, which is called ImageNet. It's essentially a challenge around building a deep learning neural network model that can perform well on the task of recognizing the contents of natural photos. At that time, these researchers put together these neural networks, combined with large amounts of training data, with a lot of compute using GPUs. And they were able to get a performance on that task that showed a dramatic decrease in the error rate to roughly around 15%, where previously the state-of-the-art just 1 or 2 years before was about 30% error rate. So since then, the AI field hasn't looked back. They've just worked continuously on computer vision, as well as other tasks in language and language translation, speech transcription, speech generation, and so on. However, this core AI technology around deep learning is still moving at a tremendous rate, and it's more important than ever for developers and data scientists to stay current with this pace of technology development. It's possible to be generations behind in just the blink of an eye. So we're doing work in IBM Research to help move from this, what we call narrow AI capability on deep learning, to one where we have more applicability to enterprise problems and problems within different industries. So where deep learning is so powerful, it also has some shortcomings. It works very well when we can have a single, well-defined task, and we can have large amounts of training data for that task. So when we can fit that definition of narrow AI, deep learning is really the tool of choice to knock it out of the park. However, when we look across different industries, when we look at what is really needed with AI in different applications and enterprises, actually it doesn't look like narrow AI. We have many, many tasks. We don't always have a lot of training data for what we want to learn. Let's take an example of computer vision and wanting to recognize visually defects in manufacturing. In that case, we often don't have a million examples for what we want to learn like we do for ImageNet. We may only have 1 or 2 examples of a defect. So it puts new requirements around learning from less data, being able to support a wide variety of tasks across many different data domains. Also, the systems in practice for enterprise, they need to be more than just accurate. They need to be fair. They need to be explainable. They need to be robust to different variations and distributions in the data, and so on. And I'll talk about this one a little bit more. Also, we need to go beyond this powerful learning capability. We need to also incorporate reasoning together with learning. In some sense, it's fulfilling the whole promise of artificial intelligence in order to really address the complex tasks that we have in practice. So let me talk a little bit more here about how we're structuring our agenda at IBM Research around artificial intelligence. So on one hand, we have this core AI where the technology is being developed so quickly, and there are a lot of advances that are still needed around the core AI. For example, around learning more from less, around mastering language, because language in particular is so important for enterprise applications, and neurosymbolic reasoning. I'll explain these a little bit more in the next few moments. But around this core AI, we also need to make progress on what we call this layer of trust. We need to build support around these algorithms to ensure that they are fair, that they don't have unwanted bias in what we learn, that these algorithms are robust to different variations in the data that can often trip up the computer in ways that they wouldn't necessarily trip up a person looking at that data. These models also need to be explainable. And by design, deep learning and neural nets have created something which are so complex, it's not always easy to understand what's going on in them and to have the right interpretation about a decision that's coming out. Since so much of deep learning is meant to drive decision support, it's more important than ever that these models, that these AI systems that use deep learning are explainable, that they're bridging this gap. We also need greater transparency, which is some visibility as to how are these models trained, what data is being used to train them, and how those models should be used in practice. So we call this the layer of trusted AI. Now further around that, of course, we have all of the requirements about how do we really put this trustworthy AI into practice, and we call this scaling AI. And this is about managing and operating and automating the entire life cycle around AI models and around these AI applications. So I'm going to talk a little bit more about each of these three layers, and I'm going to point to some of the work that we're doing at IBM in IBM Research, and then we'll conclude. So I start with one good framing for how we should think about requirements of learning more from less. There will be continuing pressure as we rely on algorithms like deep learning to do just that, learn more from less. And when I say learn more, of course, this means being able to handle more sophisticated tasks, be more accurate, and so on. But the cost cannot be so high that it becomes infeasible and impractical to learn more. We want to be able to learn from less data, less effort, and less expertise. And a way to think about this is we really want to shift this learning curve. And the learning curve here is something that may or may not enter into the region here of desired performance. We may simply not have enough training data in order to get to that region of performance. So it's really about using different techniques that will shift this curve so we can get into that region of performance by doing less. Now, one of the important applications where we need to apply those kinds of techniques, but we also want to advance capabilities overall, is around language. And in particular, improving the understanding of language for different enterprise applications. One of the recent works that we've done at IBM Research on language is something that we call Project Debater. And it's really a continuation of a sequence of many grand challenges that IBM Research has done in the area of artificial intelligence. Now, the goal of Project Debater was to build a system, an AI system, that was powerful enough that it could be given a controversial topic and a position pro or con, and it could go and research that topic and come back with arguments, either pro or con, as assigned for that particular topic, and then enter into a debate with a person on that topic. So we made some really incredible advances in order to fulfill the requirements of Project Debater. And it's just one of those example projects that happens to pull through so much in terms of technology requirements that it's really allowed us to take a big step forward in many ways around natural language processing. And that includes techniques for having a better understanding and modeling of human dilemmas and being able to form arguments around those dilemmas. It also allowed us to put focus on what we call listening comprehension, where a lot of the field has been working on reading, looking at documents as written, but not necessarily how they're communicated verbally, how people actually present and may put different emphasis on the words. So here in Project Debater, the computer needed to not only understand the text of what someone was saying, but how was it being said, understand this persuasion. And of course, Project Debater had to be able to deliver its own presentation, its arguments, and so on. So there's so many good examples of the way core technology in AI is moved forward. One place where we're working now to continue the advances is where we have tasks that combine language and vision. And this is where we're putting a focus on a technology that we call neuro-symbolic reasoning. So the idea is that there are many tasks that require us to answer questions, for example, about something that we see in a visual scene. It turns out deep learning is not very good at this. It's hard to train a single neural network, for example, that could answer questions, for example, what is the shape of the object closest to the large cylinder? Now we know that deep learning can actually parse the scene very well, and it can It can distinguish the different objects, even count the objects and so on. But to actually answer the question, the logical question here, it requires a different kind of reasoning. So with neurosymbolic reasoning, what we've been able to do is, instead of focusing the deep learning on answering the question directly from the image, the deep learning models first parse the image, and then they generate, using their models, a program that will answer the question. So this is a great combination of using the power of learning together with a more, might even think, more traditional approach for using logic and a process to solve a task. So it really points to the future of where neurosymbolic reasoning can go. So I want to talk a little bit more about this next layer, which is what we call trusted AI. So I talked about fairness and explainability, adversarial robustness, transparency. All of these are really important, because if we cannot rely on our AI models in practice, if they're not trustworthy, then we have a huge gap here between what we're able to do in the lab and fulfilling what we need in practice. So I'll say a little bit more about each one of these. So around fairness, IBM Research is moving forward this topic in a number of ways. One is creating a toolkit that we call AI Fairness 360. And what this toolkit is, it's an open source toolkit that implements more than 70 metrics and checkers for fairness. A lot of things can go wrong when we train a deep learning model. We may have a data distribution that's just not representative of what we need in practice. We may have a data distribution that doesn't account for all of the diversity that we need as we put these models into practice. This fairness toolkit includes also what we call bias mitigators. These are essentially algorithms that can go in and they can work on the data itself. They can work on affecting the algorithm itself, where the classification is occurring, and they can work on the outputs of these models. There are a number of industry tutorials included with the toolkit that developers and data scientists can really go and study and put it to practice. Explainability is another important dimension of trust here. And similarly, IBM Research has released something that we call the AI Explainability 360 Toolkit. And this toolkit is really aimed at bridging this gap from this great power in deep learning, these very complex neural networks, and what people need on the other end, who want to make decisions based on the output of these models. So it's really about designing ways to help communicate what is really going on in the computer's thinking, and how that can then be interpreted by the person on the other end of that algorithm. It includes 8 state-of-the-art explainability algorithms. It includes a number of metrics, and similarly includes various tutorials that are excellent for developers and data scientists to go and try out. One more example I wanted to give here is something that we call the Adversarial Robustness Toolkit. Now, there are some strange artifacts with deep learning that come from its ability to focus very acutely on fine details in your training data. So while we can often get an overall performance and an accuracy which is really quite amazing, when it does make mistakes, it makes mistakes in a way that often people don't make mistakes. And this is often something that challenges the trust that people have in these AI systems. So for example, by taking an image of a cat and just adding a little bit of noise to it. Now, we wouldn't say that the image on the right side here is not a cat, yet the computer can easily, by adding a little bit of noise, make a mistake and all of a sudden think that cat is an ambulance. That's a mistake we would never make. But the computer's making that mistake. And that's hard for people. It challenges our trust in these models, even if overall they are more accurate. So the Adversarial Robustness Toolkit includes a number of algorithms built into it that help ensure, by processing the data in advance, by including different checks in the training itself, to ensure that these AI models, when they are developed, that they are robust, to these different kinds of variations. And they may even be different kinds of attacks on the model. So I talked about these ways in which we're advancing this layer of trusted AI around the core AI algorithms. Now there's one more layer which is extremely important here because data scientists can train all the AI models in the lab that they may think they need, but once you put them into practice, you always find that the requirements somehow are different or are changing. There are many different conditions, for example, that we can think of, for example, like drift, where the distribution of data that we see in practice starts to move away from the data distribution that we had when we train. So we have a whole life cycle here that we need to worry about when we train these AI models. So we can think of tools and platforms that support this life cycle, but we can also think about different ways to automate this whole process of training the models, gathering the feedback, and having this loop here. And this is what we call automating AI. But I just wanted to say a little bit about how we're doing some work to advance this life cycle and the tools and platforms to support it. So data scientists and developers, they need these tools and platforms. And IBM provides many in Watson Studio and Watson Machine Learning and Watson OpenScale. And where IBM Research is focused tremendously is incorporating a lot of these elements of trust into those tools to support that whole life cycle and the continuous improvement. But I wanted to point out one other example where we need to challenge some of the thinking and approach for how developers and data scientists are working together to go from these models to deployment. And one is the great need to incorporate the key performance indicators of your application into the process of training the models. So to give an example, data scientists may be hyper-focused on creating a speech transcription model that can be very accurate and have very low word error rate for a customer care system. So this way, a customer can call up, they can ask a question or they can ask for help in some way. And the data scientist may be focused on, well, how can I ensure my speech model doesn't make any mistakes, is perfect. But what may really matter in practice is, well, for the service provider, what is the call deflection rate? Like how well is the system performing in answering those questions? And that's what really matters, not necessarily the word error rate. So we have a bigger loop here that we need to address as we feed back the application requirements into the work that we do in data science. And IBM Research is working on a number of techniques that bridge this bigger loop here. And one of the technologies that we're using is something that's called active learning. So with active learning, the data scientist is given feedback about what items they should focus on labeling in order to improve the performance of the model or the overall system. So the innovation here is to include these key performance indicators as metrics to feedback in order to do the best labeling to achieve what's needed in practice and deployment. So I wanted to conclude here and again, just point to this overall agenda. We have this core AI space. IBM Research is intensely focused on achieving a lot more technology advances in artificial intelligence. They are in core AI. But importantly, we're working very hard to build this layer of trust around these algorithms so we can ensure the development of trustworthy AI applications in practice. And we're also working to advance the technologies here to enable scalable AI. And that includes ways to support this entire AI lifecycle, as well as bringing more automation and engineering practices into the development of AI models, as well as AI systems. So thank you for listening today, and I hope to meet you soon.